Venix. Oh, Venix.
Yes, so
Was Kayade Bego Ali cooperating with
I'm
me.
yes.
So, go to the group and then tell the squad that they should start joining in now. Yeah.
Is it the middle premium?
Yeah. Tell them that they should start joining now because people are here, but they are not. So yeah, it's 6:58, but they should still join us. Okay, so Mr. Venix, you've passed on the information here.
Yes.
All right, so Mr. Venix, here's another thing you should do. Please take the email, go to the meeting options. There is a link there, forward it to our platforms. Don't worry, even if it gets leaked, only those who have been added as participants can join. Do not be tempted to add anyone in the lobby. Anyone in the lobby probably hasn't paid, that's why they are stuck there. So those who will go right through the system, they are the ones that have been approved. So check that.
Yes, I'll do that.
All right. Okay, good evening, everyone. Welcome to the first session of the IT makeup class. We will be doing statistics and probability today. We will be starting from lesson 1A, and then we will follow through just as the lessons are supposed to be. Try to be as attentive as possible. And before we dive into the lesson, here's a little word of advice before we start doing the calculations and whatnot. You should understand that statistics is just like any other an aspect of mathematics. And then that being said, it involves a lot of calculations. For statistics at our level, one thing that you should always look out for are the formulas. Mostly statistics appear quite hard to work with due to the formulas. You can see how big they look and then how complicated they can seem. But when it comes down to it, actually calculating on these formulas is not hard. It's actually simple. So the problem comes down to understanding and interpreting the formulas. If you are able to interpret the formulas, then you will be able to work the calculations. That being said, despite the fact that these calculations are easy to do, doesn't mean that they are not bulky. The calculations also take a lot of space and time to work. But once the concept is understood, they are quite easy to follow up. So it's what comes down to the interpretation of the formula. I will be explaining the formulas in simple terms when we come across them, and also we will be using them to solve questions every now and then to test our understanding, and so that we can make or we can get the full benefits of the session. So once again, welcome and good evening. So we start now. If you have any questions, raise your hand and then you will be allowed to speak. All right, thank you. So we begin now. Okay, so we'll be looking at random variables in this session. We'll be looking at the definition of probability, the definition of probability in terms of its as a relative frequency, and other ways probability can be defined, as well as agents of probability and properties of probability too. And then we'll be looking at expectations. If time permits, we'll be looking at expectations when we get that far. All right. So now the purpose of this session is to equip students with the basic knowledge and skills in probability. So in this session, all learners taking part, you'll be introduced to the basic concepts. So this is just an introductory lesson. You might see some of the things to be very simple, yes, because it's introductory. Random variables and expectation of random variables as well. So at the end of the session, you should be able to define and differentiate between random events and then random variables, state examples of random events and variables, define the expectation of a random variable, compute the expectation of a random variable using a given probability. So these are the learning objectives, and then they are the lesson aims that you should try to focus on getting before the session comes to an end. So at least if you don't get any, should get the key points. So you should know how to tell what a random variable is and how it differs from a random event. You should be able to give examples of these events and random variables. And you should be able to define the expectation of a random variable and also calculate this expectation as a probability function. So let's do a little reading, shall we? So it says an experiment is a process of observation. We are familiar with what an experiment is in science. We have discussed experiments and whatnot. So we are familiar with how we acquire knowledge through experimenting. We do this by setting events and then observing how the events play and then taking record from the event. So then since statistics on its own is also a science, an experimenting process is also applied. A random experiment is any process of observation or activity in which the results cannot be predicted with certainty. So when you talk about a random experiment, you are not able to tell what the outcome will be. You know that there is a possibility of something happening at the end of that event. But as to whether that thing will definitely happen or not, you are not sure. A perfect example is when you toss a coin. Two things may happen. You cannot say for certain that it will land on heads. That is provided it's a fair coin. Unless you have a coin that you have altered in some way, and then it's actually able to only show heads and it doesn't show tails and whatnot. Yes. Right. So then, random experiments, you cannot predict with certainty what will come out of it. So you may say that there might be heads or tails, but you cannot say definitely that there might be there will be heads. What this means is that you may be able to predict, but your predictions will not be accurate. They are just based on what you think might happen. Exactly. Alternatively, an experiment or random experiment is any specified set of actions where the results cannot be predicted with certainty. So it still goes on the same thing. So a random experiment is a specified set of actions where we cannot predict the outcome. Each repetition of a random experiment is a trial. So when an experiment is done over and over and over and over again, we are doing trials. So let's say you are tossing a coin a number of times. Tossing of the coin becomes the random experiment. Now let's say you toss the coin once, then you toss it twice, then you toss it 3 times, then you toss it 4 times. That random event has been done 4 times. Therefore, you have done 4 trials of the event. So the trial is the number of times you repeat the random experiment, not the event, sorry. The trial is the number of times you repeat the random experiment. And then the random experiment on its own is the process that you are doing to take your observations. Typical examples of random experiment that we will commonly be using is the roll of a die. So rolling dice, very common in probability. The toss of a coin. So when you toss a coin, the outcomes. Selecting a ball at random from a box containing 3 balls marked A, B, C. So you can see obviously that all these experiments, you cannot tell for sure what will come when you roll a die. You cannot say for certain what will come out when you toss a coin. You cannot say for sure what will come out when you draw a ball at random from the back. Same applies to when you have a deck of cards and you shuffle it and you draw one card at random. You cannot say for certain what the card you have drawn is. Now, in describing an event, the following terms are employed. So look at these terms carefully. The first term we have here is outcomes. So the first thing we have here is outcomes. So an outcome here. So now what is an outcome? We'll come to that. Then we also have events. Now these words, just like they are in English, most of them hold their meanings still when even you come to statistics and then probability. And then also we have an event. So what is an event? And finally, we have sample space. So what is the sample space? Now, the outcome is the result you get out of an experiment you conduct. When we talk about tossing coins, what may be the possible outcomes? You either get a head or you get a tail. So the outcomes are the possible result that you can get from a given experiment. For a random experiment, the outcomes cannot be predicted with certainty. They can only be guessed, but not predicted with certainty. An example is when a fair coin is tossed once, the result is either a head or a tail. These are known as the outcomes. Now let's move on. An event is any collection of outcomes, and a simple event is an event with only one possible outcome. An event is any collection of outcomes. So when we toss a fair die, the possible outcomes are getting 1, 2, 3, 4, 5, or 6. Putting a bunch of these outcomes together gives you what you call an event. So if I ask you what's the probability of obtaining, or what is the possibility, since we've not gone deeper into probability, let's use possibility for now, and then know that there's a difference between possibility and probability. Okay, back on it, probability, let's go. So what is the probability of obtaining an even number? This means that you have to consider the set of even numbers, right? The set of even numbers becomes your event. So when you go through your sets, how many of them are even numbers? That is an event. So then currently what you have here is a collection of outcomes. So a collection of all the possible even numbers that may come out. That becomes your event. If I ask you what's the probability of you obtaining a multiple of 4, that is an event. The multiple of 4 here, the only multiple of 4 here is 4 itself. So the event in itself will just be a set of 4, as you can see. So the collection of one or more of these possible outcomes is an event. Now let's go to the sample space. The sample space, and it's mostly represented as a capital S, of a given experiment is a set that contains all possible outcomes of the experiment. Okay, I'll take that again. The possible outcomes of an experiment put together in a single set is what we call the sample space. Let's go back to our die experiment. When you decide to toss a fair die, the faces that you may get are 1, 2, 3, 4, 5, 6. All these possible outcomes make up what you call your sample space. So know the difference. The sample space embodies all the possible outcomes that you may obtain. However, when you toss a die once, even though there is a huge sample space of possible outcomes, you may only obtain a single face in a single trial. So then know the difference between the sample space and then the outcomes. Possible outcomes, one in a trial. However, the sample space contains all the possible outcomes that may come out of your trial. Now, a sample point, and know the difference between a sample space. Sample space is denoted by a capital S, whereas a sample point is a small s. Now, it is defined as one possible outcome of a random experiment. So, for example, when you toss a fair coin, just once, when you toss the fair coin once, your possible outcomes are heads or tails, and that becomes your sample space. So you may either get a head or tail on your toss. However, the particular phase that you may obtain, whether it's a head or a tail, just one of that becomes a sample point. So a sample point is a possible outcome in a given random experiment that's inside the sample space. Now, note that a set with one sample space is often referred to as an elementary event. Note that a set with one sample point is often referred to as an elementary event. So if you take an elementary event, when you go into it, there is only one sample point present. So there may not be more than one. It is just one sample point. Now, let's move further. A set A is called a subset of B. You are familiar with set theory, and you are going to need to employ your knowledge of set theory in probability, so do not forget it yet. We know what subsets are. When you say one set is a subset of another, it means all the elements of the mentioned sets can be found in the sets, the other sets that it has been related to. In this case, we are talking about a set A and B. If we say A is a subset of B, it is denoted by this symbol right here. This here. It says A is a part of B. What this means is that every element in A is also an element of B. So a subset of B is a set that has every single element that are present in B. Let me rephrase that. A subset is a set that contains elements that are present in another set. Exactly. And then also, in most cases, the subset has fewer elements than the set it is mirroring. So it does not have all the elements that the other set has present. So any subset of the sample space is called an event. So if we take a subset of the sample space, just as we explained earlier, if I toss a die, I may get 1, 2, 3, 4, 5, 6. If I ask what are the probability, what are the odds of me getting a 2 or a 3 or an even number, your events is going to be what you are going to take out. So what's the probability of me getting an even number? You are going to have to fish out all the even numbers from your sample space. Fishing them out will give you a set of 2, 4, 6, and that set will be referred to as your event. That event, since the 2, the 4, and the 6 are all elements of the bigger set B, you will conclude that the smaller set A is a subset of B. So now, take a good look at this. It says that we have our sample space to be 1, 2, 3, 4, 5, 6. Let's say set A has elements 2 and 3, but set B has the elements 1, 2, 3, and 4, like this. We can say that set A is a subset of B, and the reason is that all the elements of A, that's your 2 and then your 3, are also present in set B. And then it's not just the elements of set A, but there are actually other elements that are present too. So you can say A is a part of B, but B is not a part of A. Then we can conclude that A is a subset of B. Know the difference between these two events. Let's say set A had elements 2, 3, and set B had elements 2, 3 as well. We would say that the two sets are equivalent. It means they have the same elements, but we will call both sets subsets of the other. Yes, so we can say A is a subset of B, B is a subset of A. That's provided A and B have the same elements and the same number of elements. But in this case, you can see that even though the elements of A are present in B, not all the elements of B are present in A. Therefore, A is a subset of B, and it ends right there. The sample space S is always the subset of itself. That is, S is always a subset of S. Now, since S is the set of all possible outcomes of the experiment, it is often referred to as a certain event. If I ask you this, you are tossing a coin. How sure are you that you will get a head or a tail? So now for this question, raise hands if you would like to give an answer. How sure are you that you will get a head or a tail? On a scale of 1 to 10, how sure are you that you will get a head or a tail if you toss a coin? On a scale of 1 to 10, how sure are you that you will get a head or a tail? Pay close attention to the keywords being used, or a tail. Now you are tossing a coin. What are the odds that you obtain a head? Right, all right. So looks like there are no hands. So, all right, okay, Mr. Freeman, you may speak.
On a scale of 1 to 10, I'll say a 5.
5, okay. So he says on a scale of 1 to 10, the chances or the possibility of you getting a head or a tail is a 5. That's what he says. So a 5 halves 10, right? That means that's a 50-50% chance. Do you agree with what he says? What's the probability of you getting a head or a tail when you toss a fair coin once? Okay. So Mr. Evans, please, you may speak.
So I guess since a coin has two sides, since it has two sides, we only have two options for it to show. And so you have one side and the other side. So if it is 100%, that would be 50-50. And so what our brother said is right.
Okay. All right. Mr. Jed, your hand went up, but it went back down. If you would like to speak, let's hear you. Oh, okay. Kayum, if you speak.
Fine,
Yeah,
it's
okay.
fine. Yeah.
It's fine. All right. Mr. Kayum, you may speak. You may unmute and speak, Mr. Kayum.
Okay, sir. It's half.
How, man? Okay. Thank you. So thank you for all your contributions. So then this tells us something, right? So then let's see if our answers are correct or if there is a problem. So now, whenever we are talking about probability, there are some keywords that you should always take note of. You should always take note of them. The words or and the word and. Or and. Whenever you say or, it means events can happen. What is the probability of you getting a head or a tail? It's actually 100% and it's a 10. Now that is a certain event. The question didn't say what is the probability of you getting a head or the probability of you getting a tail. It says the event of both happening, not at the same time, but what are the chances that you may get a head or may get a tail? That is 100% certain. The reason is that when you are tossing the coin, the sample space is your head and tail. The probability of you getting either a head or a tail is a fixed point, and then it is certain that when I toss the coin, I am either getting a head or a tail. That makes it certain. Now, if I ask what is the probability of you getting a head, that will answer your question. That will make your answer correct, 50%. What's the probability of you getting a tail? That will make your answer correct, 50%, because they have equal chances of happening. But then when we say what's the probability of you getting a head or a tail on a single toss, a head or a tail on a single toss, what this means is that you can either get a head or a tail and then it still qualifies to answer our question. So that being said, there is 100% chance. So then it's a certain event. So what this means is that the sample space, that's head and tail, in itself is always a certain event. So if I ask you, when you toss a coin, what's the probability of you getting 1 or 2 or 3 or 4 or 5 or 6? You may get any of them. So that probability is 1 because it is a certain point. So you will say you are 100% sure that you get that. So then know the difference between this and then always look at these keywords. The words and or, they will also guide you a lot when you're doing probability calculations. You just have to observe to see. Sometimes it will not be stated directly in the question and or. But when you look at the question, you realize that this one requires me to use and. It follows a different path of calculation. This one requires me to use or. It follows a different path. So then the reason why we say the sample space is always a subset of itself is because every element in the sample space can happen. Therefore, if the sample space has the events 1, 2, 3, 4, 5, 6, another sample space will always have the same events 1, 2, 3, 4, 5, 6. Therefore, the sample space is always a subset of itself. They are the same. And that being said, every event in the sample space can happen. So if I ask you what's the probability of either A or B happening, where A or B are all present inside the sets, then you conclude that that's 100% thing. It's definitely happening. So please, does that make it clear? I'd like to see if there are any questions before we proceed any further. So keep that in mind. If the question uses or for events, for example, in this one where they said head or tail, consider the fact that the only possible events are your heads and tails. And since they said head or tail, it means we don't want just the head, we don't want just the tail. We are asking you that what are the chances that when tossing the coin, you can get a head or get a tail? And that's 100% chance. Because if I toss it, I get a head. It is true, head or tail. I did get a head, is correct. If I toss it, I get a tail. It is true, head or tail, I did get a head. Okay, Mr. Emmanuel, yes, please, you may speak.
Yes, sir. Please, in probability, is it possible for the word if to be used?
Is it possible for the word if to be used?
If.
Like if.
Yes, yes.
Okay, so now, the words if, don't restrict yourselves to the words or and, okay? Or the words and or. If it's used inside, mostly it doesn't hint to a calculation. But then for conditional probabilities, when they use if, then it means that it is telling you to calculate for a condition. And we are going to go to conditional probabilities later. So yes, if also hints to a particular, what do we call it, line of calculation that you will have to follow. And that will be for conditional probabilities. And we are yet to get there. Okay, yeah. But then for the basics, you should know that at the foundation or at the roots of probability, you should always consider probability and probability or in order to be able to calculate. And these are the things. So once you are able to interpret the formula and you can tell whether they want and or an or, you will always be able to follow through. For the basics of probability, we will just be using simple fractions. So we'll be using simple probabilities. But when we go further in, some probabilities, in order to calculate them, you are going to have to use a probability and another probability, and that's when things get complicated. But then understanding the formula or interpreting the formula makes everything simple. So when we get there, stick with me. Like don't be stereotypical and say in class it has been confusing, so it will probably be the same. It's not necessarily the case. When it comes to maths, it's always about how you think. The way you think will mess you up in maths. Okay, let's proceed. So now, Find the sample space for an experiment of tossing a coin repeatedly and counting the number of tosses required until the first head appears. So we are finding the sample space. Remember, the sample space is the collection of all the possible outcomes that may happen. This question is about a coin toss, but you should be careful about how you read the question. You see, the question is not asking about whether you will get a head or a tail. No. It says that find the sample space, that's one, of an experiment when you toss a coin repeatedly and you count the number of tosses required until the first head appears. So now if we were here in person, I would take a coin and toss it. Now the question is, if I toss the coin on my first try, I may get a head, right? So on one try, I may get a head. So it means they said we should find the number of tosses until the first head appears, and we should state the sample space. It may be on the first toss, I may get a head. So then in the sample space, there could be a 1. 1 is a possible outcome. There can also be the event that when I tossed it the first time, I didn't get a head, but when I tossed it 2 times, I will get a head. This means the first head appeared on the second toss. That means 2 also becomes an outcome, a possible one. It may also be that on the first second, I didn't get it, but on the third, I did. This will mean that my sample space will keep going on forever. You see that the question didn't specify an end. It didn't say what is the probability that when you find a sample space for tossing a coin 4 times, it just said repeatedly and counted the number of tosses required. This means it can even take you 1 million tosses before your first head will appear. So you can see that when they drew, so it says it is easy to realize all the possible outcomes for this experiment at the terms of the sequence 1. So maybe on 1 toss or on 2 tosses or on 3 tosses. But that's the sample space is given by S is equal to 1, 2, 3 to infinity, to positive infinity. So what this means is that you may have to toss a billion times before your first head appears, but you may also have to only toss once. So since it's a random experiment, we cannot predict the outcome. So as far as we are concerned, we are tossing. And then as we keep tossing, the outcomes that can come can be, we can get the first head after 6 tries, we can get it after 10 tries, you may get it after the first try. But you cannot add 0 to this particular sample space. So for some sample spaces, 0 will be included. But the question is, they said, when you are tossing, can you toss a coin 0 times? That's impossible. Right. So keep that in mind. So are there any questions before I proceed? Mr. Emmanuel, please, will you be doing this for me? Please monitor those who raise their hands and then alert me when it's needed. Okay, thank you. All right, let's proceed. So now, let's consider an experiment of drawing 2 cards at random from a bag. The bag contains only 4 cards, and then the 4 cards are marked with the integers 1, 2, 3, 4. We have to find the sample space, S1. So we are saying we are going to find different sample spaces. So we are going to find the first sample space of the experiment. If the first card is taken out and it is not replaced, we should let the first number indicate the number of the first card drawn. So we are going to do this before we move. Find the sample space S2 of the experiment. If the first card is drawn, the first card drawn is replaced before the second. All right. So let's take that question carefully. So I'm going to share my whiteboard now. So forgive me if it takes some time to display, okay? So now we are considering an experiment, and in the experiment, we are drawing 2 cards at random from a bag. So let's say we've given you a bag and then we've put 4 cards in. Each of the card has a particular label on its face. One is labeled as 1, the other is labeled as 2, the other is labeled as 3, the other is labeled as 4. Now the question is that if we decide to remove a card at random from that bag and we do not put it back and we take another card outside, what is the probability that, what are the sample spaces or what are the possible events that may occur? So now here's what it's going to look like. So please, can you see my board? Mr. Emmanuel, please, can you see my board? Is Mr. Emmanuel here? Okay. Mr. Felix, okay, yes, okay, I can see your answer. Okay, thank you. So now, here is my sample space. Let's try to see what we are going to get. We have a bag, it has 4 cards. The possible cards in there are 1, 2, 3, 4. If we pick a card at first, right? It could be a 1, it could be a 2. So what I like to do for this is I'll draw a table. And then it will be easier to interpret the results from this table. So now let's put in the first or the top column what we may get on our first pool. So we may get a 1, we may get a 2, we may get a 3, and we may get a 4, right? If we try the experiment again, let me expand this table a little, sorry. So for the first try, let's put the events of the first try up here. And then let's put the events of the second try over here. We may also draw a 1 for the second try. We may draw a 2, we may draw a 3, we may draw a 4. We may. Now, let's see the combinations. If I pick the first card, remember, if we take the card, you see the question was specific. It says, and not replace. So it means that if I take the first card, I'm not going to replace it back. We are trying to find out all the possible outcomes. Remember that putting all the possible outcomes together gives you the sample space. So we are going to take the first card out. If we take the first card out and the first card is a 1, remember, if it's a 1, it means 1 has been removed totally from the bag. So it cannot be picked again. So it may be a 1 on the first try. And then secondly, okay, so then, sorry, here, let me clean that. All right. Good. So since when we pick a card, it cannot be 2 of the same card, we may first pick a 1 and then we may pick a 2. But we cannot pick a 1 and a 1. So over here, it's impossible. Remember, we cannot pick a 1 and a 1 because it says when we pick the first card, we do not replace it. We may also pick a 1 and a 3. So maybe the first try can be a 1 and the second can be a 3. We may also pick a 1 and then a 4. It's also possible. So in the first try, we may pick a 1 and a 2, a 1 and a 3, or a 1 and a 4. On the second try, sorry, so it may also be that our first card was not a 1. It was actually a 2. That's possible, right? And then we got a 2 and a 3. A 2 and a 1. Okay, let's cross them like this. It may also be that our first try gave us a 2. And then, okay, so since we cannot take the same of a card 2 times, it's impossible to get a 2 and a 2, right? So let's cross that out. But the possibility of we getting a 2 and 3, it can actually happen because we can pick a 2 first and follow it by a 3. And we may also pick a 2 and then a 4. It's very possible. Another event that may happen too is when we start picking 3s. We may pick a 3 and a 1. We may pick a 3 and a 2. But we cannot pick a 3 and a 3. And this is mainly due to the fact that once we pick the 3, there will be no more 3s in the bag because we didn't replace it. But we may pick a 3 and a 4. Very possible. We may also pick a 4 first and pick a 1. Or pick a 4 first and pick a 2. Or pick a 4 first and pick a 3. But it's impossible to pick a 4 and a 4 since we are not replacing the 4 we picked. So now let's see our sample space. The sample space becomes the possible set of elements that you are seeing here. So please, is the board clear? If you can see it clearly, yeah, so that's the board. Let's see what our sample space is from the board we see over here. So our sample space S will be equal to the possible set of events. The first one, we can get a 1 and a 2. Enoch entry. All right. Yeah, Enoch, please go ahead and ask your question. You may unmute and speak.
Yeah, I was wondering if you could move that thing, what is written on the white to the middle there, because I'm not seeing it clearly. I mean, can you write that in the middle? We see it clearly.
All right. Okay. So you are not able to see the board I'm sharing clearly, if I get you right.
No, I'm seeing the board, but what is written there? I think there's something
Covering.
in it. Prince Nanadapo is broken. Yeah, I mean, it's knocking the thing written there.
Oh, okay.
So kindly move it to the middle.
All right, I'm coming. So, Mr. Jojo, please, are you facing the same problem still?
I think your board is not loading.
It's loading. Oh, okay. Sorry.
Yeah.
Mr. Evans, please, you may speak.
Yes, sir. Mr. Jojo, I think your network is lagging a bit.
Why, Mr. Evans?
I had the same issue. I mean, this thing bar where the options came on the screen. So you were talking and making reference to the board, but the options, the menu of the whiteboard had covered it. And so if the network is lagging, when you have removed it, use another person may still see it if the network is lagging a bit.
Okay. So here's what I'm going to do. I'm going to try to. Is it okay now?
Yes, please. Thank you.
Yes. But is anybody else having the same issue?
Please, Madam Mona was facing the same issue.
Yeah. Is she fine now?
I don't know.
Okay. Right. So as I was saying, we are
But
listing the set.
is she in the session? Sir, please. Sorry. Is she in the session, please?
Yeah. Is she still present? Let me
Yeah, she
check
was
that.
in the session, then she was facing the same issue. So I told her she should like exit, then rejoin.
All right.
Oh.
Okay. Let's move this up here a little. So I believe you can still see though, because I just want space to be so I can write. So you can still see. Okay. So let's continue. Please, can you see the board fully still? Okay, we proceed. So now the possible outcomes are this. So now that we have used our table, we can clearly see what the outcomes are. So we know that the first draw may be a 1 and the second one may be a 2. We also know that it's also possible that the first draw might not have been a 1. It may have been a 1, yes, but then it was followed by a 3. We can also see that it may have been a 1 and a 4. Or it could have also been a 2 and a 1. Or it may have also been a 2 and a 3. Or it may have been a 2 and a 4. All these possible events, it may have also been instead of a 2 and a 4, as you can see from the cells, a 3 and a 1. It may have also been a 3 and a 2. It may have also been a 3 and a 4. And it may have also been a 4 and a 1. It could equally also be a 4, a 2, or it could be a 4 and a 3. This is the event that when we draw one card, we do not replace it. So this means every card has only one chance of being picked in a single draw. So when we do the trial one, we pick 3 and 1. That's all there is to it. So then if you count this, we can count this. So our sample space is the set of all these possible outcomes. And then the values in there are 1, 2, 3, 4, 5. So let me use this. So then we have 1, 2, 3, 4, 5. There is 6. There is 7, 8, 9, 10, 11, 12. So there are 12 possible outcomes from the draw. So what this means is that the sample space is the possible outcomes we have here. And the reason why we only have these ones is because when we draw, we are not replacing. If we were replacing, that would mean when we draw the 1 the first time and put it back, the second card may have also been a 1. So we could have gotten a 1, 1. It could also be that when we draw, we might have drawn a 2 first, and since we replaced it, we could have drawn a 2 again on the second try. So since the question says you are drawing a card and not replacing it, the possibility of getting a 1, 1 is 0. You can't get a 1, 1. You can't get a 2, 2, because once the 1 was taken out, it didn't come back. So I hope this clarifies things for this side. Now let's move back to the questions. Let's move back to the, what do we call it? The slides. And then let's continue from there. Right. So now it says that, so we have done that, and then we've gotten all the possible sets of events that could come. So it could be 1, 1, whatever, all the way to the end. Now it says, second question said, find the sample space S2 of the experiment if the first card drawn is replaced before the second one is drawn. So find the sample space of S2 of the experiment if the first card drawn is replaced before the second one is drawn. So now, look at the solution A, the question that we just worked. You can see that for the sample space 1, when we drew the card 1, the one that followed was card 2. We may have also drawn 1 and 3, 1 and 4, 2 and 1, 2 and 3, 2 and 4, all the way to the last. But for the second one, that's S2 over here, the possible values that we can draw, since we are drawing a card and also replacing it, we may have gotten a 1, 1. We could have also gotten a 1, 2. We could have gotten a 1, 3. It could have also been a 1, 4. It could have also been a 2, 1. It could equally be a 2, 2. So you come to see of having a repeated event is there. Because when we draw a card, we replace it. So we may pick that card again. So then the sample space has differed from the first set to the second. In S1, we only draw and then we don't replace. But in S2, we draw and replace. This one, first sample only gives us how many possible outcomes? 12. Second one gives us 16. So the first one gives us 12. The second one gives us 16. All right. So now, find the sample space for the experiment of measuring in hours the lifetime of a transistor. So for this one, if you are measuring how long a transistor can last until it gets damaged, since we do not know, we can only estimate, or we may say that this transistor might just run forever. So what this means is that its lifespan can start from 0 and go all the way to positive infinity. So it says clearly all possible outcomes are all positive real numbers. There is no way you can have a number of years in the negative form. So you cannot say I'm negative 6 years old. How is that possible? Maybe you traveled back in time. So it doesn't happen. So it's impossible. So there's a sample space S for this experiment will be given as S equals 0. So it says that x is such that it is 0 is less or equal to the value of x, but x is less than infinity. So this means that we do not know where exactly s will stop, but we know that it is not endless. Because as far as it's a device, it will definitely die someday. We just can't predict when it will die. It might be in a million years or a billion. We can give a reasonable estimate and say about 100 years, but it just might go over. So then it's 0 for the starting points, but for the end points, we do not know. This brings us, so it's a foreshadowing to the next concept, discrete and continuous sample spaces. A discrete sample space is one that has a set of values that can be finite in a given range. For example, if we walk into a room, like a classroom, and I ask you, how many boys are in the class? There is a fixed number that you can give me. For example, if I ask you to tell me that there are 50 people in the class, and I say between 1 and 50, how many boys are there? You can only give me a fixed number because this is a real number that is countable and it's not one that is measured. So it can only take on particular values in a given range. We call such values discrete. On the other hand, we have continuous ones, and continuous values are values that are mostly measured. And these ones, they can take on any particular value in a given range. So for example, if I tell you that measure the temperature of your rooms right now, if I say everyone should measure the temperatures of their room right now, I may measure 36.1. Someone may measure 36.11, depending on how precise the thermometer is. Someone may also measure 36.111. Someone may measure 36.21. So even just between 36 and 37, the range of values in there is infinite, because since numbers are infinite and then decimal numbers are also revolving around the same digits, you can have positive decimal infinity. You can keep counting from 36.9, 36.999999999, it's endless. So then these ones are continuous and they are mostly measured values. So mostly when you take a measurement of something, how long a pole is, how tall a tree is, how hot water is, what the atmospheric temperature is, how old someone is, even age. Yes, age is considered a continuous variable, depending on how it's calculated, but under normal circumstances, time and age are considered continuous. What this means is that your age can also take on any range. Mostly we round off our ages. I tell you that I am 30 years old, I am 35. That's a rounded estimate. Because when it comes down to it, if I want to calculate the months in between, months that have passed my 30 years, or months that I am to 30 years, I will be 29 point something, or I'll be 30 point something. So what this means is that just like other values, your age itself can also be considered a continuous variable. Sorry. You go into a room, you count how many black shoes are there. That is a discrete variable. It's discrete because you can predict there are only a fixed number of balls that can be in that bag, or a number of shoes that can be in that room. You cannot go and have an infinite number of shoes. So you will definitely count and stop somewhere. So a sample space is discrete if it contains a finite or countable infinite set of possible outcomes. So even if the set of possible outcomes is endless, as far as you can count what you need in there, the possible outcomes in there, then it is a discrete one. Now, in this case, the elements in the sample space can be listed, or the list does not terminate, as in example 1. So when we go back to the example 1, it says that, where is it? It's example 1. Good. In example 1, it says, it's easy to realize all the possible outcomes for this experiment in terms of the sequence 1, 2, 3. However, you can see that this event is endless and it's never going to stop. But that doesn't mean that the event is a continuous event. It merely has an infinite sample space. But all the possible outcomes can be counted. You cannot count how hot water is, but you can count how many values you get when you toss a coin to get a head. So we can toss it once and we count once before we got a head, or we might have counted twice. Since this is possible for this to be counted, it is discrete. But then for the events like your age or something like temperature, these ones cannot be counted. Therefore, we say they are continuous. A sample space is continuous if it contains an interval, either finite or infinite, of real numbers as seen in example 3 above. So what this means is that if you take a sample space, it can be just from 36 to 38. But if it is a continuous one, the values in between can go to positive infinity. You can have 36.0, 36.01, 36.011. It's just endless. So that makes it continuous. A random variable usually is written as x. A random variable usually written as x is a variable whose possible values are numerical outcomes of a random phenomenon. So what this means is that if we do a random experiment such as tossing a coin, we may get a head or a tail. That becomes a random variable. So the random variable, your head or your tail, are only possible because you are doing a random experiment like tossing a coin. So random variables result from random experiments. Alternatively, you may say that a random variable is a variable whose value is unknown, or a function that assigns values to each of an experiment's outcomes. So then its outcomes, we do not know for sure, but we are sure that there will be an outcome. As for that, we know. So like in the case of tossing a coin, we cannot predict for certain that there is going to be a head, there is going to be a tail. But we know that there will either be a head or a tail. So the outcome is certain. We just can't say it precisely. Random variables are often designated by letters X, Y, or Z. And they can also be classified as discrete, which are variables that have specific values, like what we looked at in the case of counting the number of coin tosses it takes to get a head. Or continuous, which are variables that can have any values within the continuous range, like the temperature of a body at a time, or the temperature of the room you are in right now. It can assume any value in a given range. A typical example of a random variable is the outcome of a coin toss. If the random variable y is the number of heads we obtain from tossing 2 coins, y could be 0, it could be 1, or it could be 2. This means that we could have no heads, we could have 1 head, or we could also have both heads on a coin toss. Let's explain that a little. If I tell you to take a coin and toss it now, and then take just 2 coins, and then you toss it, how many heads will you get? The possible values you can get from your toss are maybe head on the coin on coin 1 and head on coin 2. So that's head. Let's do a small display for this. All right. So we are tossing a coin. We're tossing 2 separate coins. So let's say the first coin is coin 1 and the second coin is coin 2. If we toss both of them at the same time, we may get a head and a head. We may also get a head and a tail instead. Or we may get a tail and a tail instead. Or all these ones here talk about what the possible outcomes can be from the double coin toss. So we are either getting a head and a head and a tail and a tail. The arrangements could change. We could rather have a tail and a head or something. All these ones are different. We'll come to that later. However, the question is not referring to that. It's asking that if I toss the 2 coins twice, if I toss the 2 coins once, how many heads can I get? I can either get 2 heads here, as you can see. From the head, it's obvious. So I can either get 2 heads here, or from this side, I can get 1 head, or from this side, how many heads do you see? No heads. What this means is that the sample space for this particular experiment, S, is going to be equal to 0 heads, or 1 head, or 2 heads, as you can see here. So then for this random experiment, the number of heads that we can get is limited. We can either get 2 heads when we toss and we get lucky, or we can get 1 head and the other will not be a head, or we can get 2. This particular one is not continuous, it's also discrete, and it's a random variable because you do not know what the outcome will be. That is why when we are doing it, we give 3 possible outcomes, because we do not know what exactly it might be. We just know that it could be a head-head, head-tail, or a tail-tail. Okay, please, can you hear me? Am I audible?
Yes, sir.
All right. Okay, let's continue. So then keep that in mind. Yeah. Okay, so give me a few minutes. I want to check this and then I'll be back. Yes, 2 minutes. 2 minutes and I'll be back. Okay, I believe you can hear me now. So please show thumbs up if you can hear me. All right, then let's continue. So keep that in mind. We can see this, and then the reason is because we are tossing the coins, and when we do it, we may get a head-head, we may get a head-tail, we may get a tail-tail. Therefore, the number of heads in the first try may be 2. It may also be 0, it may also be 1. So the sample space becomes 0, 1, 2. All right, so with that in mind, let's move back to our slides and continue from there. All right, now examples of discrete random variables include the number of children in a family, the Friday night attendance at a cinema, or the number of patients in a doctor's surgery, or the number of defective light bulbs in a box of 10. So what this means is that you can see that all the values they are giving you here can be counted. So all these values that can be counted are values that are considered discrete. So now without wasting any more time, I'll just go straight to you and I'll ask you to give me an example of a random variable that you will consider as a discrete one. So think of your answers, I'll come to you. And let's move on to the continuous. Continuous random variables are usually measurements, and examples are height, weight, the amount of sugar in an orange. They can assume any value or the time required to run a mile. So all these ones are random, but they are continuous. The first set, they were random, but they were discrete. Second set, they are random, but they are continuous. So now my question to you is this. Give me a continuous random variable that you can think of and that has not been mentioned on the slides. So then hands up if you have any ideas on that, and then let's take it quickly. If you would like to try that, just raise your hand and then. Also, I'll have to start calling people. I'll have to start calling people. All right. So think of your answers so that I can call someone. Okay. Let's call those who have not said anything today. Vida. Yes, Vida.
Yeah, hello. Good evening.
Yes.
Yeah, please, the question again.
Right. An example of a continuous random variable. An example of a continuous random variable.
Please, no idea.
No idea. All right, that's fine. Joel, Mr. Akota Joel, powerful name. Yeah, what's an example of a random variable that you can think of? Mr. Akota is here in name, but he's not here in person. Okay, Mr. Oscar Ajemai, what is an example of a continuous random variable that you know? Your mics are allowed, by the way, so you can just tap and speak. Okay. No idea. Okay. Please, is there anyone with an idea of what's happening here? Please raise your hand because looks like everyone has no idea. Mr. Freeman, speak away. Mr. Freeman,
The time taken to charge your phone.
the time taken to charge a phone. Excellent. Mr. Joel, you may speak. Mr. Joel Akota, you may speak. Oh, okay. Mr. Richard Rue, you may speak. Everybody's ghosting me. Okay, Mr. Evans, please speak away.
The temperature of a room.
The temperature of a room. Yeah. Temperature of a room in degrees Celsius is a continuous random variable when it is taken. So keep that in mind. So Mr. Richard, is it that you have a question? If you have a question, please, you may go ahead and ask. Oh, okay. Mr. Richard is not feeling like talking today, so he will grace us with his brilliance the next time. Okay, let's proceed. So yes, the examples you gave were right. The examples you gave were correct. So now, chance of probability. Sorry. Mr. Richard, your hand is up again. Oh? Yes, please ask if you have a question. Or his mic has been disabled because it has been allowed. Okay, let's move on. Chance and the assessment of risk play a part in everyone's life. We as men, most of us, right? I'll not say everybody, I'll be general. You do a lot of things that involve risk taking. Yes, Madam Vida, please, you may speak.
I want to say height.
Hi, excellent. How tall, right? That is also
Yes,
a
please.
random variable. Thank you for that contribution. So measuring how long or how tall something is also a random variable, since it can take on any single value, even in a short range, such as between 1 and 2. It may be 1.1 inches, 1.11 inches, 1.111 inches. It can be as long as whatever, can be as short as whatever, and even it can be short. Compare two of them together. One is just a little longer than the other, another is just a little longer than it. So it means the values they can take on in a given range are infinite. So you cannot predict what they can assume. Not easily, unless you reference another object, and that is still measurement. Right. Good. So as I was saying, as boys, you take a lot of risks. A common example is, since we are in this match seasons, we do betting. The bettings that you do are also risk taking. Some of you actually do risk assessments, and then you go under this, under 2.5. This, you understand the situation, so then you use that for your betting. Others also go and then they stake the bets on other things. They just go full into the match. Chelsea for win, and then Chelsea loses. The probability of Chelsea winning was 50-50. So then risk assessment also takes into account probabilities. As a loan officer, you may want to evaluate the probability that a customer defaults, especially if you're a loan officer in Ghana. In Ghana, when people take loans, the probability of them running is way higher than the probability of them paying if you calculate other people's instances. So what this means is that if you're a loan officer, you go to an area, you should be able to assess and tell how these people respond to loans. Check previous data and see how these people responded to the loans that they took. And then you use that to assess the risk. You calculate certain things like their income. You calculate certain things like their day-to-day spendings. See whether these people are capable of turning that loan into something good to give back to your business. Then you'll be able to tell whether they will be defaulters or not. So you calculate the probability. Now, it cannot tell you for certain, but it can increase the chances of you of knowing who is right for it and who is not right. Okay, so an investment officer, you are interested in finding the likelihood of an investment resulting in a loss. Yeah. So then, as an investment officer, someone just comes to you with a random idea, or maybe we've gone to a town, and then in this town, these people here, you can see that there are not food stores here. The food stores here, there are not many. As a matter of fact, there is no joint where you can eat. And then one person pitches a business idea to you. He's like, Mr. Investment Officer, I want you to give me this amount of money to start a restaurant. And in the restaurant, we are going to fry a lot of meat. We'll be selling goat meat. Goat meat as well. Is it Shivon or what? I don't know. Right? We'll be selling a lot of goat meat. We'll be selling a lot of pig and all pork. Yeah, pork. And then you know that in this town, there are certain things that these people hate. Not like they hate, certain things they hold as taboos, like killing certain animals or eating certain things. You as the investment officer must sit down, take all these factors into account, and then find the likelihood of the business succeeding in the given environment. So you take all these things into account, and then you can do your risk assessment to tell them, nah, this is a bad decision, so I shouldn't invest in that. That being said, that bad decision can also turn around and give you a positive result. That is why probability is a chance. It only talks about the chance. It tells you how high or how low it is for the event to happen, but it doesn't tell you for certain whether the event will happen or not, unless it is a definite probability, a certain one. Yeah. All right. So now, probability has found a wide range of business applications, such as calculation of risk in banking and then insurance industries, quality control, and market research. Most events in life are unpredictable. Events in life are non-deterministic. So if you say something is not deterministic, you cannot tell the end from the beginning. You can only suggest from other experiences or from other things you know that it's going to be like this. But you cannot say for certain, coin where heads, but that doesn't mean that you actually predicted it. You merely said it may have been ahead, and it truly may have been ahead, and then it ended up being ahead. That doesn't necessarily mean that you know the event, so it becomes deterministic. No. If the world is treated as stochastic, then we can measure the chances of any particular outcome happening in a given situation. If we treat the world as all things being equal in certain events, so for example, if I tell you that tossing a coin gives 1/2 for heads or 1/2 for tails, I am assuming that when I toss the coin, my outcomes will just be a head and a tail. However, consider the fact that if I decide to toss the coin more than once, the experiment is going to be repeated countless times, and each trial will give me a different number of heads and a different number of tails. Therefore, if we are not treating all things equal, the probability then changes. Theoretically, a theoretical probability says that when you toss the coin, you get 1/2. But the experimental one says that if you toss it, you may get 5 heads and only 2 tails. So the probability changes from 1/2 to something like 2/7 for the tails. It changes. So then if we treat the world as all things being equal, we can sit back and measure probabilities for almost everything that occurs. And when we say all things being equal, yes, we still consider some variables. So it's not just the experimental ones we calculate and the theoretical ones. It goes beyond that. Okay. So a theoretical probability is basically one that considers all things being equal, whereas the experimental one is a probability that actually does an experiment, takes data from the experiment, and uses that to calculate a given probability. All right. Probability is the measure of the likelihood of the occurrence of an event. So if I measure how likely something is to happen, I've done the probability. Probability of an event can be thought of as the relative frequency of the event. So the relative frequency just talks about one frequency point over the total. So for example, if we go into a class and then we say that 5 people, let's say there is a class of 20 students, and we say 5 people are 5 years old. Let me use another age. Let's say 5 people are 4 years old. And we say we are to calculate the probability of taking a 4-year-old from that class. We are going to need the number of 4-year-olds over the total number of ages, or the total number of years. The total number of ages will still be the total number of people in the class. So over the total number of ages in the class. So that will be the 5 people who are 4-year-olds over the total. Whenever you do a part over a whole, a sample point over the sample space, the number of values in the sample space, we have what you call a relative frequency. So if you go back to your frequency tables, you realize that when you're calculating relative frequency, you take the individual frequency over the total frequency, and it gives you the relative frequency. The probability of an outcome can also be interpreted as a subjective probability or degree of belief that the outcome will occur. So it can also be defined as how much you believe that this event is going to occur. Like, what are the chances that the world will end tomorrow? Most of you are going to say it's very low. Others are going to say it's very high. But then when you look at it from a point of view, well, for the end of the world, we cannot predict it. But if you take factors into account, maybe there is a meteor approaching Earth. Scientists calculate that it might miss the Earth by a few inches. The probability of the world ending is there. You can actually calculate it because things could go wrong. The meteor can actually come towards the Earth and damage everything. So then it becomes a belief system. You believe it may happen or may not. So that's when probability may be a degree of belief. It still doesn't change the fact that it's a relative frequency, because that belief can equally be measured as a relative frequency as well. Probabilities are always numbers between 0 and 1. What this means is that you can have values that are probabilities. They will always be from 0 to 1, but they will never be an event that is beneath 0 or above 1. So you cannot have a negative probability, and you cannot have a probability that is greater than 1, or a probability that is an improper fraction. You can't. So an event with a probability 0 has no chance of occurring, and an event with a probability of 1 is certain to occur. We will do the axioms of probability. Before we go and look at those confusing lines of maths, use this as your understanding. The first axiom of probability says that probabilities are always from 0 to 1. So it's not just between 0 to 1. 0 is the probability that the event cannot occur, and 1 is the probability that the event will definitely occur. So then, an event, that's the first axiom of probability, that the probabilities are always between 0 and 1, or from 0 to 1. The second axiom says that an event with probability 0 has no chance of occurring, and then an event with a probability of 1 is certain to occur. Other definitions of probability are the relative frequency and the classical definitions. The classical definitions are the ones we are used to for calculations. An example, the probability of an outcome is interpreted as the limiting value of the proportion of times the outcome occurs in n repetitions of the random experiments as n increases beyond all bounds. I may have said a lot of gibberish. So let's break it down. So now it says, if you take an outcome, the probability of the outcome occurring is the number of times that outcome is present over the total number of times, over the total number of possible outcomes there are. So for example, I walk into a room, and in the room, there are 2 blue shoes, and then there are 5 red shoes. 2 blue shoes, 5 red shoes. If I ask what's the probability of me taking a blue shoe, it's going to have to be the number of blue shoes there over the total number of shoes. So not blue over red, but blue over the total number of shoes. That will make it 2 blue shoes over 7 shoes. The 7 shoes includes the 2 blue shoes and then the 5 red shoes. So our probability becomes 2 over 7. For example, if we assign a probability of 0.4 to the outcome that there is a defective item in a production batch, we might interpret this assignment as implying that if you analyze many items inside the batch, roughly 40% of them will not function properly. So if I tell you that there is a 40% chance that you will find machines over here that are bad, it means if you take about 10 machines, roughly 4 of them will be in very bad condition. So that's what the probability means here. It can assign values, and then the assignments can be made into real-life interpretations. This example illustrates a relative frequency interpretation of probability. As you can see, we are taking a part over a whole. So that makes it a relative frequency. So now, here is it. It says that the probability of an event A, as you can see over here, is equal to the limiting value of the possible outcome, which is n. And mind you, n can be from 1 all the way to infinity. It can be any value. That's what it means. So then when you come over here, it says, let's say we are finding the probability of A in a class where there are n number of students. So there are n number of students, and we are finding the probability that we can meet student A. N represents number. So this will be the number of A, as you can see here, over the total number of students in the class, which is n. So then probability is given as number of favorable outcomes over total number of outcomes. So if you come over here, you see it says where number of A over n is called the relative frequency of event A. So A is a part and the total is n, so it's a relative frequency. Stated differently, the relative frequency can be stated as the ratio n is of A over n, still the same thing. For the probability of A, if n is a large number. So for example, in the case of a class, 5 girls, 45 boys, ratio of girls in a class is 5:50. If you calculate that, it becomes 1:10 or 1 over 10 when you simplify it. So then it can be expressed as a ratio 2. Now, when the likelihood assumption is not valid, then the relative frequency method can be used. So then if we cannot tell for certain how the outcome will be, like in a coin toss, when we know it's going to be 1 over 2 when we do a single one, then you can go ahead and use your formula to calculate and simplify. The relative frequency technique leads one to conduct an experiment n times and record the outcomes. So if you want to calculate the probability of an event, you need to do an experiment and also take, for example, an event such as A. If you want to know the probability of A occurring, it will be the probability number of A there over the total number of things that you got. So then we say over here, that's a more simplified formula. Now, all these formulas, they may talk about different things, but when it comes down to it, they are all used the same way. So this means you can choose to memorize any of these formulas, and it's fine. Personally, this is the best. And then in statistics, you are not always supposed to state the formula in formula form. If you can state it in words, you are good to go. So then in words, you may say probability of an event, P, is equal to the number of favorable outcomes over the total number of outcomes. So it says where FA denotes the number of experimental outcomes that satisfy A. So we are looking for A, the favorable outcomes for A, and then over the total number of outcomes. So here's an example. The table below shows the frequency distribution of grades in statistics class. It says that the marks are 60 all the way to 99. If you take 60, one person had 60. If you take 75, 3 people had 75. If you take 78, 4 people had 78, all the way to 99. The relative frequency for mark 90, relative frequency of you getting 90 is computed as how many people got 90? 5 over the total number of people who took the test, 63. You see the way we are ignoring the values here, even though they are numbers. Mind you, those values are just representing the actual data we need. The same way we will go into the class and we are looking for boys or girls. This time we are looking for people who got 60. We are looking for people who got 75. So they do not concern this calculation unless we are doing expectations. We'll come to that later. So over here, you can see if we wanted to know the relative frequency of the mark 1 occurring, it's going to be 1 over the total outcomes. The total being what we get when we add all these numbers. And then when we add all these numbers, we get 63. So probability of obtaining a 60, is going to be 1 over 63. Probability of getting a 78 is going to be 4 over 63. Probability of getting an 86 is going to be 11 over 63. So basically, the number of the favorable outcomes happening. So it says 86 occurred 11 times. So if we are looking for the favorable outcome 86, probability of obtaining 86 is going to be number of 86s that occurred over the total number of occurrences, which was 63. Also, the relative frequency for obtaining a mark less than or equal to 83. Let's go back to that. So it says a mark can be less than or it can also be equal to. So what are the marks that are less than or equal to 83? If you want to contribute, raise your hand. You're looking at the screen. What are the marks that are equal to or less than 83? And how many are there? If your hand is up, you may go ahead and speak. Yes, Mr. John A. Champon. All right, let me allow you. Joshua A. Champon. All right. Yes, sir. So, Mr. Joshua, please unmute and speak.
I said the marks that are equal to less than or equal to 80, right?
The marks that are less or equal to 83. Yes. So please, how many are there? How many are there?
Have 60, 70, 78, 80, and 83.
Excellent. He says 60, 75, 78, 80, and 83, right? Mr. Joshua, is that it?
Yes, please.
All right, sir. Anyone with another contribution, the marks less or equal to 86. Remember what I said, or, so it means the mark can be less than 86. The mark can also be 86. So if you want to look at the marks that are either less or equal to 86, it includes all these values you are seeing here. So 60 is less than 86. So it satisfies less or equal to 75, 78, 80, 83. They satisfy this. Right? So then if we are talking about 86, marks less than or equal to 86 can include 86 as well, because it says or equal to. Now in this question, it says that the relative for frequency for obtaining a mark less than or equal to 83 is going to be all the events that are less or equal to 83. That's 60, 75, 78, 80, as well as 83. We are not going to take those numbers. Remember, they are just representing actual values. That's at the frequency. So then the frequency, how many 60s are there? There was 160. You take that one. You combine that with 3, combine that with 4, 5, 7. You put that together, your answer is 20 over 63, 0.31. I mentioned earlier, right? I mentioned earlier that you should consider the words or and. Some questions will require that you do a multiplication, and others will require that you do an addition, especially for basic probability of operations like this. In this question, for example, the question was a question that went with or. It says that obtaining a mark that is less than or equal to 83. So since or was used, we are following addition. So whenever probabilities are asking for or for two events, probability of events A or B happening is going to be the combined probability of A and B. So in the coin toss experiment, probability of getting a head is 0.5. Probability of getting a tail is also 0.5. That's half-half. Now, probability of getting head or tail is going to be half plus half, and that gives you 1. And that makes it a certain event. So that was the reason for the answer I gave back then. So then whenever you are giving questions, consider what the question says. So over here, what we have actually done is we took the probability of 60 occurring, that's 1, over the total number 63, plus the probability of 75, 3 over 63, plus 78, 4 over 63, plus 80, 5 over 63, plus 83, which is 7 over 63. And once we took all those values, remember, if you're adding fractions and the denominators are the same, you write all the denominators as a single value, since it's your LCM. And then you go ahead and add the numerators. So this is actually probability of 60 occurring, that's 1 over 63, plus 75, that's 3 over 63, all the way to the last one. And that is what has been written as a combined fraction here and simplified as a decimal too. So you can leave your probability in any form, percentage, unless the question specifies. So using the relative frequency definition, we can therefore estimate the probabilities. So that's the probability of obtaining a mark 90 is 0.09. Getting a mark less than or equal to 83 is going to be 0.31. So now, before we proceed, I have some questions that I'd like you to answer. So let me see if I can pull one here. So let's go down, down, down. All right, so here's one. Let me share this screen so that you can see it clearly. Okay, so now look at the question on the screen, right? And then you give me your answers. So it's a fairly simple question. I'm sure you're familiar with it. A die is rolled once. Find the result, probability that the result is a prime number. A die is rolled once. Find the probability that the result is a prime number. All right, Kayu Midriso, you may speak. Or your mics are muted. Mr. Venix, please handle the mute. Yes, sir.
It's 1 over 3.
It's 1 over 3. Okay, a die is rolled once. Find the probability that the result is 1 over 3. So he says that it is 1 over 3. So that means we have 1 over 3. If you agree with that, just say you do and then we proceed. But if you don't, raise your hand and then let's add your answers and then we can confirm whether or not this is right or wrong. Okay, so I can see 2 hands are raised. All right, so let's check that quickly and then we move on. Let's see. Okay, so we have Mr. Felix and then we have Mr. Joshua. So Mr. Felix, please go ahead and speak. Okay, 1 more 5, 8, 6. Mr. Felix, please speak.
0.5.
0.5. All right. Mr. Felix also says the probability is 0.5. Okay. Third hand up. That is Mr. Richard. You may speak.
Yeah, I had 1/2, which is 0.5.
Okay, excellent. Madam Monica.
1/2.
1/2. Okay. Is it Vida or Mr. Jed? Mr. Jed. Mr.
Yes,
Jed. Mr. Jed.
1/2.
1/2. So
Yeah,
we
one
all
over
agree.
two.
Okay. So now let's see why. So one of you care to give us the explanation why you are saying 1/2? We are clearly talking about a dice, and the last time I checked, a Ludo die doesn't have a 6 face. Doesn't have 2 faces. It has 6 faces. So 1/2 in free here. Is it not supposed to be number of favorable outcomes over total number? Yeah, Mr. Joshua, care to explain?
Oh.
His mic is muted. Okay, allow mic. Yeah, Mr. Joshua. Mr. Joshua.
So yeah, can you hear me?
Yeah. Yeah, I can hear you,
So
boss.
a little die has 6 faces. So if you throw the die once, you may get either 1, either 2, either 3, either 4, either 5, or either 6.
Okay.
So when you check this outcome, the prime numbers are only 2, which is 3 and 5. So
all right.
2 divided by 6 would be 1/3. So 1/3 is the answer.
Oh, okay. So then I can see where Mr. Joshua's confusion stems from, and I believe you've all noticed that too. So his is not with the working, but it's just with the definition of what a prime number is. So Mr. Joshua, one actual thing is that there are actually 3 prime numbers here and not 2. We define prime numbers as numbers that only have 2 factors. That's always 1 and themselves. Now, even though 2 is an even number because it can be divided by 2, 2 only happens to have 2 factors. That's 1 and itself. This makes 2 a prime number, just like 3 and just like 5. Therefore, the prime numbers here are 2, 3, and then also 5. So then these 3 values are the numbers. Okay, boss?
Yes, I understand, sir.
Yes, sir. So the probability of obtaining the prime number becomes 3 over the total, which is 6. And then simplifying this gives you the fraction 1 out of 2. 1 out of 2 because, 3 goes into itself once and goes into 6 2 times. And then others equated it to its decimal counterpart. They said it was actually what? Half, which is 0.5. So then it looks like the basics are well understood. So yes, we can go back and then continue from where we left off. So we have to move faster, of course. We can clear this. We are far into the slide, so let's keep going. Okay. So yeah, in an experiment for which the sample space S is the outcomes are equally likely, so we've talked about it. The probability of an event A is the number of outcomes in A over the total number of outcomes, or the number of ways that A can occur over the number of ways the sample space can also occur. So a number of A over number of S. In other words, the probability of A is the fraction of the total number of outcomes that cause the event to occur. So we've already explained that, so we go further. Suppose that there are 5 balls in a bag. 3 balls are red. All right. Yeah. Yes, sir. I've seen it. Okay, let's continue. So suppose that there are 5 balls in a box. 3 balls are red, 2 are black. The box is shaking and then the ball selected without looking. What is the probability that that ball is red? From what we just looked at, to calculate this probability is the number of red balls over the total number of balls in the bag, right? So we know that there are 3 balls in the bag. There are 3 red balls and there are 2 black balls. So in total, that makes 5 balls. Probability of obtaining a red ball becomes how many red balls are there? 3 over how many balls are in the bag. That's 3 plus 5, 3 plus 2, which makes 5. So the probability becomes 3 over 5, or as a fraction, 0.6. All right, here's another one. In a group of 400 college students, now this particular probability question, it is slightly different from what you can see over here. because it takes higher things into account. But then, due to the nature of the question, we can still solve it like the normal probability. But perhaps we will come back to this probability when we are doing conditional probabilities, and it will even seem more simple. Now, it says in a group of 400 college students, there are 170 science majors and 230 non-science majors. Of the science majors, 55 are women, and there are 120 women non-science majors. One student is selected at random from the group. Find the probability that the selected student is, in fact, a science major. So look at the question carefully. It has given a breakdown here. But to calculate it, it used the table. So when you are given a lot of values to manipulate, using tables will help you to easily identify the numbers. So over here, it says that if we take the science majors, 55 of them are women and 115 of them are men. If we take the non-science majors, 120 are women and 110 are men. So the total number of women is what we get when we add the science majors plus the non-science majors here. And that gives us 175 you see over here. The total number of men is men who are science majors plus men who are non-science majors, and that gives you total number of men. The total number of people in the group is the total men, women plus total number of men, and that gives us 400. First question says that, well, let's find the probability that the selected student is in fact a science major. So then, what will be your answer to this? Mr. Joshua, your hand is still up here. Will you like to answer that, or it was a mistake from the previous time? Mr. Joel, okay. Hey, let's relax. All right. So, Mr. Joshua, you go first. Okay, his hand is down. Mr. Joel. Yes, sir. Mr. Joel. Mr. Joel, or is his mic muted? Let me have a look. All right, let me unmute for you. Sorry. So, Mr. Joel, yes, what's the probability that you find a science major?
It will be 170 over 400.
Probability of finding a science major is 170 over 400. And are there other opinions here, or do we all agree with that? Yeah, okay. I can see a hand up. Okay, Mr. Joel, still Mr. Joel. Is there any other person whose hand is up? All right. Okay, then we can get back to it. So then the probability of finding a science major is just as he said. Yes, it is the number of science majors over the total number of people, which is 170 over 400. So a simple scenario here. Right. Now, what about the probability of obtaining of picking a woman? Probability of picking a woman, what will it be? So always remember to leave your probabilities in simplified forms or decimal forms. Right, Mr. Jed, yes, please, what's the probability of finding a woman in this set?
Yeah, hello. Yeah,
I can hear you, sir.
175 over 400.
Total number of women, which is 75, over the number of people who are there, which is 400. So you see, it just says woman. It doesn't specify whether the woman is a science major or a non-science major, just a woman. So now, what's the probability of picking a person who is not a woman nor a science major? So you can pick a person. This person shouldn't be a woman. They shouldn't be a science major too. So Mr. Felix, yes, answer that one for us.
0.275.
0.275. So Before we go to the decimals, can you plug the parameters that you are using to get this? What numbers are you taking into account here?
110 over 400.
110 over 400. Okay, so thank you for that. Mr. Joel Akota, neither a woman nor a science major. Oh, his hand is down. Okay. So now let's see all our answers and then let's see if they are right. Let's start with the science majors. To find the number of science majors, we have to find how many science majors are there over the total number of people. And it just so happens that the number of science majors are what we see here, 170, right? When we combine 55 plus 115, we get 170 science majors. So the total is 400. So we are going to get 170 over 400. Present. So for a woman's own, is the total number of women over total number of people present. That's 175 women over 400 people. Moving further, the next question says the probability that it's neither a woman nor a science major. What this means is that you are going to find someone who is not a woman and also not a science major. So then where are the people who are not women? They are down here in this section where we have men. And where are the people who are not science majors? They are in this column where we have non-science majors. So for someone to not be a woman, they should be in this row of men and in this column if they are not science majors. And the only number that qualifies for that is this value here, 110. No. Yeah, sorry guys, there was a call came through, sorry. Okay. Okay, let's proceed from where we left off. So the total number of so that's it for the non-science majors. And then finally, the neither woman nor science major, that's 110 over 400, and then you simplify it. Okay, so it looks like we have a strong grasp of the concepts already. Yeah, we are good students. So as you can see here, the working has been outlaid. And in every instance, you see how they are stating the formula a little before they proceed. Yeah, okay. Now, let's talk about the axioms of probability. So axioms are like the characteristics that define a probability. Let's talk about the first axiom. We've already looked at it. Probability is always between a 0 and a 1, inclusive. So inclusive means we are including 0, we are also including 1. So technically, it's from 0 to 1. So you can see it says it's less or equal to the probability of a value. And then that probability of the value may also be less or equal to 1. This means it can be 0 all the way to 1. So as you can see here, that's the first axiom. This will help you to work questions. When you are solving and you realize that my working is giving me a probability of 5, it's wrong because probabilities cannot be above 1. Second axiom says that a certain probability, like a probability that is bound to happen, like we know for sure that this thing is definitely going to happen. Like if I give you a coin and then the coin only has heads on both sides, what's the probability of obtaining a head? That's going to be a certain event. So it's going to be 1. Because no matter how you toss it, what you are going to get is 1. So if the front face is 1, back side is 1, you put both 0.5s together, you still have 1. Second one says the probability of an event not occurring or an event not being present in the sample space will always be a 0. So the probability of an event not occurring is a 0. Probability of an event that is not in the sample space occurring is also a 0. So if I ask you when you toss a die, what's the probability a fair 6-faced die? What's the probability of obtaining a 7? Your answer should be 0 because there are no 7s in the sample space. Therefore, it's a 0. In performing an experiment, we assume that the results will be one of the simple outcomes. In other words, we assume that the event S will occur. So it can't happen that something in the S will also occur. So that's always 0. Third axiom says that if you are combining two probabilities, and this is where the OR comes in, probability A or B, that's A union B. If you are putting them together and the two events are mutually exclusive, mutually exclusive means probability of A happening does not have anything to do with probability of B happening. Then, if you are finding these two events, you can just add them together. We're going to look at an example right now. Let's go back to our Ludo die experiment, shall we? So I want to use this screen. So I believe you can see the screen, right? Yeah. So now, the screen I'm sharing right now, let's say this is our Ludo die and our sample space is 1, 2, 3, 4, 5, 6. If I ask you what is the probability of getting a 1 or 2, what's the probability of obtaining a 1 or 2 when you toss a Ludo die? This is actually going to be the probability of you getting a 1 plus the probability of you getting a 2. So you're going to write this, in other words, as probability of you obtaining a 1 union probability of you obtaining a 2. So probability of 1 or 2 happening like this. To solve for this, you are going to have to know probability of 1 occurring. So what's the probability of 1 occurring here? There is only a single 1 here, and then there are 6 possible outcomes. The probability of a 2 occurring is also just a single 2 out of 6 possible outcomes. So then the probability of 1 or 2 occurring is going to be probability of you getting 1, which is 1 over 6, added to probability of you getting 2, which is also 1 over 6. So putting these two together, your answer becomes 2 over 6, right? Which in other words is just 1 over 3. Now, the third axiom we were looking at says that the probability of me getting a 1 does not affect the probability of me getting a 2. Therefore, we say these two events are mutually exclusive. So when you're finding the probability of two events that do not affect each other, to find the joint probability, you can just go ahead and add them. However, if it happens that the two events have a midpoint, like a point where A and B also occurs. So for example, if I ask you, what's the probability of obtaining a prime number or an even number? This changes the case because when we take prime numbers, all we have are the values 2, 3, as well as 5. And if we take even numbers, what we have here are 2, 4, 6. So let's say the probability of obtaining a prime number is giving us the probability of P. No, P is not a good one for prime. So let's say probability of getting a Z is prime number. And then that is 2, and the sample space there, it is 2, 3, 4, 2, 3, 5. So then the probability is going to be equal to number of prime numbers there are, which in this case is 3, over total number of outcomes there are, which is 6. And that equates to the simple probability of 1 over 2, or in other words, 0.5. The same, give me a second, sorry, my phone is going off. I have to plug its emails. Okay, are we still alive? Ah, it's gone. Right, Mr. Freeman, please, can you hear me speak? Okay. Yeah, sorry, Mr. Freeman, can you hear me?
Hello. Hello.
Oh, yeah, all right. Sorry.
Yes, sir.
Yeah. Okay. Sorry, my network was cut abruptly. My phone went off, so I had to plug it in and come back online. So please, I'm sorry, it's 8:57, but there are some end of units exercises that I want us to do. So for the sake of that, I would not like us to close. So if you could give me 10 minutes into the time, let's get back on track and do those end of unit exercises for the sake of this lesson before we end. So please, the participants still present. So please, the presenters, please, the organizers, please coordinate them. Oh, it's called. Okay, so please, the meeting, give me just a few minutes and then we'll get back on track so that we can continue. Just about 2 minutes. I want us to answer the end of unit questions before we stop. Oh. Okay, so sorry, we are back online. All right, so please, thank you for staying. Yes, yes. So if you can hear me, please let me know. Mr. Freeman, please, can you hear me?
Yes, please, I can hear you.
All right. Thank you. So we will end here today, but we will tackle a little end of unit exercise together, and we'll just be giving the questions. So get your pens and papers ready. The question will just be displayed, and then you give the answer, and we look at the correct answer and we follow up. So I'm sorry for the disturbance. My phone went off. It says I was giving hotspot from my phone to my machine, so it went off. So I had to plug it in and then get back online. So sorry for that. I'm glad it happened so close to the end so that we didn't have to miss anything. So please, all those present, please, if you are present, give a reaction so that I can see that you are present so that we can continue with the test. Okay. So, Mr. Freeman, are hands up that I can't see, or are reactions given that I can't see, or they can't hear?
They can. I'm sure. I'm not. I don't know if they can hear, but I can hear you clearly.
You can hear me clearly. All right. Thank you. Then I guess.
I hear you.
Mr. Joshua, can you hear me?
Yes, sir.
Oh, okay. All right. Thank you. Madam Monica, can you hear me? Uh, Mr.
Yes,
Kayumi Drisu.
please.
All right. Okay. Thank you. Thank you for the response. So as I said, without wasting my time, let's get right into it, and then let's do the end of unit exercises. So review what we have covered so far. We only answer questions on what we have actually covered so that we won't do too much. So here's my screen. Yeah, let's move into it. So we start from question 1. So now, define a random experiment. Provide 2 examples that are not found in the slides. So define a random experiment and provide 2 examples that are not found in the slides. Define a random experiment and provide 2 examples that are not found in the slides. So just raise your hand and then we tackle that quickly so that we can move from here. Okay. Yes, so the hands. Okay, then let me just call because our people are not reacting. So let's start with Mr. Kayu Idrisu. So please, you may unmute your mic and speak. You don't have to give a straight definition since this is just a math course, but you can just tell us what a random experiment is in your own words or what you know, understand about it, because we just covered that. So let's see.
Okay. So random experiment is just what I understand. Your explanation is that I would like to give an example.
All right, we like that. We like that.
So, like, I don't know the number that we are, but I hope we are like 30, taking an experiment of 30, what do you call it? 30 people in a class.
Okay.
I think that's one of the examples.
Oh, okay. So taking an experiment based on the number of people in a class is a random experiment. Okay. That's a good one. Okay, that's perfect. So he has given the example, he has given one. So then what is a random experiment? Who can define it in better? So now he has given the examples. That's the second part of the question. He has given one. So now what is a random experiment? Mr. Felix Freeman, would you like to try that? Mr. Enoch, entry, you are next. So prepare your answer down. Mr. Isaac Kwenu, I'll come to you too. So please prepare your answer down so that when we come, it's just fast.
Okay, from my understanding, a random experiment is an experiment whose outcome or possible set of outcomes is undefined. We don't know. Yeah.
Oh, okay. That's the perfect definition, actually. Thank you, Mr. Freeman. People, clap for him with your reactions. And that's the exact answer that we wanted. So a random experiment is an experiment whose outcomes are not known or are not easily predicted or are undeterministic in nature. Okay, so now examples of random experiments, Mr. Enoch Entry. What are the example of a random experiment you know? Okay, Madam Monica, what is an example of a random experiment you know? Okay, Mr. Anthony, what's an example of a random experiment?
Hello.
Yes,
Can you
sir.
hear me?
Yes, please, we can hear you.
Can you talk of measuring a distance?
Measuring a distance, that is an example of a random experiment, yes. So measuring a particular distance is a random experiment because maybe from the onset, you do not know what you are going to measure. unless you are doing it based on another. So maybe you can see that this thing is as long as this other thing. That technically means you have done the measurement. So it is still a random experiment, else you wouldn't have known if you didn't measure. So he's right to say that. Okay, so tossing of a coin, we already know that picking a particular card from a deck of cards, as he said, measuring an object, measuring the weight of something, all these are random experiments. So a random experiment is a process in which the outcome cannot be predicted with certainty. An example is drawing a card from a standard deck or measuring the daily rainfall in a city. These are all random experiments. All right, let's go. So now, next question. A box contains 5 slips, numbered 1 to 5. One slip is drawn at random. List the sample space. So then the box contains 5 slips. One slip is drawn at random. The slips are numbered 1 to 5. List the sample space. So what are the possible outcomes? Put them in a set and then give them back to me. So think of it. What are the possible outcomes in a set and give them back? So just think of it in a few seconds and then you raise your hands and we answer. Guys, our time is up, so let's do this fast. And these are simple questions, so just try and then we go. Okay, right. So then the possible answers to that question are a sample space is 1, 2, 3, 4, 5. So all the possible outcomes that will be drawn from this guy will be 1, 2, 3, 4, and 5. Another question. A coin is tossed until a tail appears. Write down the sample space for the number of tosses required. So write down the sample space for the number of tosses required until a tail appears. Okay, Mr. Freeman, please, you may go ahead.
Okay, the sample space will be 1, 2, 3 to the nth toss.
Okay, 1, 2, 3 till the end. So then it's infinite, right? So it says write down the sample space for the number of tosses required to get a tail. Excellent. So to the nth tail. So I like that you included that. So till the infinite number of tails. So then as you can see, the possible outcomes are from 1 all the way to positive infinity because you don't know where it ends. Good. Next question. Define a random variable. Okay, we've talked about that. Distinguish between discrete. Okay, yes. Define a random variable. Distinguish between discrete and continuous variables. Let's keep the worded one. So random variables, so variables from random phenomena, or a numerical outcome from a random phenomena is a random variable. We know that already. So discrete random variables, they take countable values, whereas the continuous ones are measured in an interval, like temperature. If 3 coins are tossed, let x be the number of heads. List the possible values of x. Good. So this one, I'll try Mr. Joshua. Consider the answer and then give it back to us. Say you toss a coin 3 times. No, you toss 3 coins once. What are the number of heads you can get on a single toss? What are the possible outcomes for heads you can get on a single toss? Mr. Joshua. Okay, Mr. Enoch. Mr. Oscar. Zebibia Edin Postal. Wow. Madam Monica. Mr. Felix. All right. Yes, please.
Number of heads that can be gotten is 0, 1, 2, and 3.
0, 1,
That's
2, 3 is the correct answer. Excellent. So then let's look at it. So yes, the possible values are 0, 1, 2, 3. And this is mainly because your outcomes may be for the 3 coins at a go, you may get head, 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 or you may get head, tail, head, or you may get head, head, tail. Okay. No, sorry. So head, tail, head already covers that since we are just counting how many heads. Or you may get tail, 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 or you may get tail, tail, head. So what this means is that you can have 3 heads, as you can see. You can have 2 heads, as you can see. You can have no heads, as you can see, 0. Or you can have 1 head. So thank you, Mr. Freeman. That was the correct answer. All right. So it looks like Mr. Freeman, if this was a score-based payment something, Kawaji's canning now, of course. A die is rolled once. Define a random variable y as the square of the number shown. List the possible values of y. So now let's say when we roll a die, we are going to take a random variable y, and that y is the square of any of the faces on the die. So it means we can take any of the faces and square them, and then that can be y. So y can be the square of 1, square of 2, or any of them. What is the possible values? What is the sample space of this experiment? This is a very interesting question, by the way. So what's the sample space of this experiment? So let's do this question and do the next one, and then we are done. So yes, what's the sample space of this experiment? Mr. Joshua? Mr. Enoch? Oh, okay. Then let's just dive into it. So the sample space of this experiment will be this. Since we are taking any of the faces and squaring them, yes, Mr. Freeman. Yes, please, let's go.
Okay.
Yeah.
Okay, so say the possible outcomes will be 1 to 6. The square of individuals events in the sample will be
Yes,
1,
please.
4, 9, 16, 25, and 36.
Good. 1, 4, 9, 16, 25, 36.
Yes,
You couldn't have
please.
said it any better. Perfect. Wow. Mr. Freeman, he knows his stuff. So then, as you can see, the possible outcomes are truly 1, 4, 9, 16, and then you might ask yourself why. So 25 is included. The reason is that he said y is a squared face, like it's one of the faces of the die squared. So it can be 1 squared, 2 squared, 3 squared, all the way to 6 squared. So then the possible values of y can be 1, 4, 9, all the way to 36. All right. So the last one, as I said, state the classical definition of probability. Okay, so it's a definition type. So it's what we mentioned earlier. For a value A, the probability of A occurring is the total number of ways A can happen over the total number of ways the sample space can happen, where n of A is the number of favorable outcomes and the number of S is the total outcomes. All right, we have come to the end of our session. And then I would like to end right here. I'm sorry for the network cut that happened during the last few minutes. I can assure you that it will not happen again. So we have come to the end of the lesson. Thank you for your time. And as you can see, the lesson has been very rewarding. This is the basic parts. As it goes further, even more complex concepts will be made easily understandable for you. All you need to do is be ready to learn and dedicated to the study. Thank you. I will put these question slides on the page, and then you can attend them your own time. They are there with the answers as well. Thank you for your time. It's a night, and that's a wrap. Goodbye. And before we leave, Mr. Evans would like to speak to us, but a big number of us is not here. So I believe we can do that meeting on our WhatsApp platform. Mr. Evans, please, is that fine?
Yes, so we will remind those who are here and also remind on the pages as well.
All right.
Yes, so